Okay, thank you all for coming. Sorry about any hassles that you may have experienced in getting here and into your seat. We decided actually to simplify the panel format, so I'll get into that a little bit later, partly because of all the other chaos. But our topic is architectures for big data analytics and data mining platforms. So really interested in the architecture part. The idea for this panel came when I was working on a project with Sony Global recently. We were looking at architectures of big data analytics systems. I'll just try to speak more into the microphone. Is that better? Okay. Well, Ron, you should have that one. Okay, so I wanted to have a quick survey of the state of the art of these kinds of platforms. And so I went out on the web, and there are lots of resources available there, but there are also meetings happening in the Bay Area especially, where you can actually see glimpses of people's architectures. And so, you know, there's a new data mining group starting up in San Francisco, and there are a lot of other groups like that having meetings. You can see a glimpse in presentations that are really about something else, but people are being more open about what they're doing, I think, nowadays, and they're sharing what they built. And I think that's actually really healthy, and it helps a lot of people get up to speed more quickly. And there are some conferences like the Hadoop Summit where you can actually see a whole bunch of them at one time. I thought it'd be a nice idea to have a panel on this where we had a bunch of people show a bunch of different architectures. And in this panel, we've actually got some people who have experience with more than just one architecture. So Ron has a company that builds these kinds of systems for lots of other companies. And so he has experience with more than just his own company's architecture, although he does have like a reference architecture that he maybe prefers. So you'll get to see a bunch of different architectures in a short period of time. And that's the format for the panel. We're just going to go 1, 2, 3, and the panelists, you know, ideally in a panel like this, you don't want to have PowerPoint, but it's hard. You know, an architect wants to see an architecture. It's hard to do that without some kind of slide or picture. So we do have some PowerPoint, but we're going to go through that just 1, 2, 3 down the row here from left to right and get that out of the way, and then we'll open up to questions. And I'll start that off with 1 or 2 questions that I have, and then we'll field questions from this room and also the other room. Okay, so Ron, I'm going to hand it over to you.
All right, thanks, Paul. So here, before I get into the diagram, maybe just a little more background on me. I'm founder and CEO of Think Big Analytics. We're a little over 2 years old, and we're a professional services firm that's purpose-built for big data. We created the company just to help customers use data engineering and data science techniques to create value. You know, as part of that, as Paul alluded to, we work with a number of large enterprises, helping them take these techniques that were shaped right here in Silicon Valley and apply them to the messy real world of the enterprise, right? That we sit here in the middle of a campus where many of the big data barbarians have created these new technologies that are changing the way the world works with information. And at Think Big, our mission is to bring that fire to enterprises, to large companies, whether they be retailers, financial firms, media companies, in advertising, in telecommunications, et cetera, and make these successful. And while there's some differences from the tabula rasa of a startup, there's what struck me is how many commonalities there are in the kinds of approaches and techniques and architectures that are applying in the enterprise to what's been working over the last few years in the online arena. Now, prior to starting Think Big, I was VP of engineering at Quantcast. Jim and I worked together for several years there and before. You know, had the opportunity to be part of being very early in big data, working with Hadoop and data science techniques, leading both application development and data science efforts. I won't talk a lot about Quantcast because Jim not only can cover that well, but of course has all the latest details. But that experience was very important in us coming up with what works and what doesn't in this space. So with that in mind, just two more quick things, and I'll turn to the diagram behind me. One is that Think Big, we're a professional services firm, so we partner with leading product companies like Cloudera or MapR or DataStax to put together best-of-breed solutions to do the data science, the data engineering, creating value. And the other thing is we are hiring. So if you're interested after this talk, please make sure to look us up on the web and feel free to send me an email at ron.bodkin@thinkbiganalytics.com. Now, with that quick overview behind us, this diagram is how we like to think of really a reference architecture for big data. So we see that when you're working with these data mining systems, these advanced analytic systems, there's really the interplay of both near real time and more batch systems. So the horizontal axis here is latency, where on the left really represents low latency, and on the right represents higher latency. And then the vertical axis has to do with the kinds of interactions. On the top is more transactions, events, interacting more with direct transactions or activities. And then on the bottom is an analytic axis, more of consideration, decision support, looking at information. So what we see is part of what's happened over the last few years is that the data processing systems, the analytics systems, have unbundled the fictitious database of the 1980s, the single place where all information is being held and managed. And you're now dealing with systems that explicitly have different roles and responsibilities on different cycles. So we see Hadoop as a batch platform for housing massive amounts of data, for allowing you to do complex analytics on that data, do exploratory analysis on less structured data as kind of a foundation for big data, and that is in the bottom right of the diagram here. We see that that's being used, though in tandem with a number of other technologies. So most of the time when people are using that kind of technology, they're doing data mining, deep exploration of the data inside of Hadoop. They're doing data science to test out models and to refine them, and then push information into lower latency environments. Those could be lower latency analytic environments like MPP databases. They could be lower latency NoSQL environments for doing quick scans and doing more ad hoc analysis on unstructured data, both of which represent create a process of exploration, visualization, understanding data, and perhaps most compellingly for creating value, it's integrating into live environments where there's actually systems responding to events, to transactions. So creating profiles, creating information about the value of an impression, creating a score on the health of a system, so that when an interaction comes in from outside, that model can be quickly applied and responded to. And that, of course, is a feedback loop, that you have a process of creating automated models that then get applied in near real time, often with some updates to state that are happening in very low latency. And then the results of those interactions are captured and fed back into the central analytics environment to refine the models, to analyze and improve. So we think that the biggest opportunity ultimately in big data is around creating these automatic loops of processing information to create insight and to automate response. But to support that takes a lot of rich visualization and tools to do analysis. So in the diagram, you can see some of the different components we think are important. All right. So it's green. How about that? Not the usual red. The notion of having Hadoop as an environment, we do call out Hadoop because most of the capabilities in this diagram are still very much up for grabs. We don't know what the standard's going to be in 5 years. The one technology in big data that we're very confident is going to become a standard is Hadoop for the batch processing. Its approach to MapReduce, we think, is well established, and it's as a foundation for managing these cluster resources, we think is going to continue to be an important part of these architectures in future. Most of the rest of the diagram is labeled with a quality or a characteristic, but we don't feel like it's as clear what the winner is going to be, although you might say Solr is doing pretty well for distributed search. So Hadoop cluster to support a data science cycle of exploration with a variety of tools for data mining and query analytics on top of the MapReduce foundation. having some kind of a scheduler or dependency engine to drive production flows that regularly apply these models and organize pushing data out for a real-time response in the edge, as well as pulling data in for analysis, whether it be traditional structured data that's replicated in or unstructured data that might be fed in through a variety of messaging or event systems. And these tend to be integrated in with low latency access to data, whether it be search or simple key value NoSQL databases. We see the emergence of new tools that data scientists use to visualize and understand data in these systems, as well as extension of more traditional tools, often mediated by feeding results that are analyzed in a raw form in an agile way in the big data environment, being fed into more of a structured summary database for following more traditional data warehousing approaches. So in addition to this opportunity to create a lot of value by having this flow of data, data science in the big data environment, there's also a significant shift in by being able to work with raw data, full sets of data in a more raw form. Big data gives you this opportunity, this architecture gives the opportunity to assess the value of information and decide if you want to create summarized, structured data when the value of the data has been proven, instead of investing upfront in the guess of what's going to be useful or not. So that's our overall big data reference architecture. And flipping forward, we look at it another way too, though, which is what are the different capabilities that really need to come together in order to build an effective solution, right? So there's a lot of pieces here because as you mature an environment, as you add more and more to how you work, you have to answer these questions. A lot of times when organizations get started, just as in the last diagram, you don't have all of this, right? This represents a mature, sophisticated environment when an organization's been doing it for a while. So you might find your first workflow management is a cron job running a bash script, right? It might be simple, but over time, it can become more sophisticated. So we organize into different capabilities. What is the platform layer, whether it be how you set up your cluster, is it in the cloud or local, is it virtualized or real? What distributions of software, hardware and software. Then, how do you govern what resources run where? How do you give low latency access to data, NoSQL and search? How do you govern the data and manage metadata? Taking data in and pushing data out, managing workflow, transforming the data, providing what's especially the focus here, the data science algorithms, as well as beyond reporting and the whole development stack. So we see these are the capabilities, and there's patterns and approaches to each of these. Obviously, we're not going to dig into all of that in this upfront piece, but that's our general model. Now, I don't want to go through in the same level of depth a couple of examples, but it's worth pointing out this applies in the concrete to different customers, different cases, right? So here's a project we've spent a lot of time on with Network Appliance. We've done some talks in public about this next generation auto support system that we've been working with them on that is capturing a lot of data, soon to be a petabyte of data from storage devices around the world, allowing low latency response, archival and deep batch analytics, and will support rules and more sophisticated machine learning for predictive customer service and cross-selling and upselling. So that's, in many ways, an instantiation of the last diagram with more specific products and capabilities put into a real-world environment at scale with disaster recovery. So I'll leave this one up for just a sec and move on to a simpler example. This one is a project we've talked about publicly we've been doing with Newstar, where this is the architecture we started with that was more of how do you get started, how you start to collect hundreds of terabytes of data from diverse high-value data sets to enable the data science process that we've subsequently been working with them in terms of starting to do different experiments and ways of working with integrating these different data sets together. It's simpler, right? It doesn't have as much complexity. It doesn't have all of the boxes. It's integrating existing schedulers and mostly doing some clever things in terms of how to work with the data in Hadoop. But that's part of the point, right? You don't have to start with the full diagram. You can start with something, create value, and move incrementally. And with that, I'm looking forward to the discussion tonight and pass the mic over to Jim.
Will anyone be upset if I stand up?
Go ahead.
All right. Thank you, Ron. My name is Jim Kelly. I'm the VP of Research and Development at Quantcast, where I have been for this VP of Research and Development at Quantcast, where I have been for 6 years since the company started. And I'm going to be sharing with you, well, how we do what we do. And since I've been there kind of since the beginning, a lot of what I'm going to be describing is my fault. But some of it was Ron's fault. No one has ever heard of Quantcast. We're not a consumer company like LinkedIn, for example. So we don't have much of a reputation for big data, but we've been doing quite a bit of it, and we haven't talked about it much. But I managed to escape the office tonight and sneak down here, so I'm going to talk about it a little. But a little background on Quantcast. So we've been around for about 6 years. We were founded by two guys. One of them had a background in networking and building large-scale, high-performance systems. And the other had a background in doing fraud detection for big banks, which meant he had a very good sense for data mining, for pulling nuggets of interesting data out of giant sets of it. And he also had a talent for talking to big bankers, which is becoming handier and handier. And what we did initially, the first product of the company was a measurement product for online publishers, which is still the thing we're best known for. So we invited publishers to put our tag on their site, and if they did, we would tell the world how big their audience was and what kind of people went there in terms of their demographic composition or where else they went online, anything to help bring the audience to life for advertisers. This proved to be a really popular program for both big and small web publishers, and so we had over 500,000 sign up. And today we're getting one or 200,000 pixels per second that we're having to serve for measurement purposes. And that has allowed us to build a big statistical model of the internet, essentially, which is the basis of the second thing we've done. So the measurement product is free. We just give it away. But we make money by selling targeted ad campaigns for advertisers, leveraging this big statistical model of the internet. We're tied into the major real-time bidding ad exchanges, so that's another big source of data for us. So we're getting about 40 terabytes of data a day from these diverse data sources, and we've evolved our own tech stack for analyzing it. So I'm going to take you through that. This is it, and it bears. You can see a lot of echoes of Ron's division in here, because it's what we've got on is kind of three things going on. There's sort of a real-time stack here, there's a batch stack here, and then there's an analytics stack over here. All of it's built on hardware that we own. So we operate about a dozen data centers around the world. For both measurement and bidding, it's important to be geographically close to the users. And then on top of that, we've got kind of a few big things that we need to get done. We need to deliver measurement pixels. We need to execute bids on the exchanges pretty quickly. We have to run a website that produces reports and analysis for people, and then we have our own internal, more ad hoc analyses that we do to understand how the business is going. So the real-time stack kind of supports the first two use cases, and this stack, these were two big networking problems that we had to solve, and we solved them pretty well. The pixel delivery we've tuned pretty well so that we can serve measurement pixels faster than Google Analytics can. The real-time bidding works well enough that we can respond to 99.6% of the bid requests we get within 100 milliseconds, which is the the time limit, and that's a better call-out rate than anybody else on the exchange has. So we're happy with what we've built there. To do it, we're doing a fair amount of work in this real-time decisioning. So we're running campaigns for several hundred advertisers at this point, with collectively with 1,000 or a couple thousand line items, and a line item being sort of the unit of decisioning for ads. And we're considering every line item for every one of the 10 billion bid requests that comes in every day. And so there's a fair amount of math that's going into that. There's also some dynamic logic associated with the incoming stream. So we handle different pixel requests different ways depending on what we need to do with them. We may need to have to redirect them someplace, or we may want to pick up real-time signals that we want to act on quickly. So if we're doing a campaign for a hotel, for example, somebody's not going to be in the market for a hotel room for very long, so we want to be able to act on that signal pretty quickly. So the decisioning needs to do all that, so it needs to draw on kind of two different kinds of data sets. We have an in-memory data store that we use for keeping kind of these short-term signals that's built around Redis, and things get expired from that, so it doesn't last very long. So we back it up with an on-disk store that we call Keebler, and this is something that we built ourselves, and it's a proprietary binary format that is just highly optimized for scoring 1 billion cookies against 1,000 different models and being able to look them up quickly. All of this is tied together in a Storm framework, and then coordinated by what we call the real-time engine. One of the important things that we do, because this decisioning process and the ability to optimize campaigns is so core to the company, we organized a little differently than a lot of companies doing this do. I think a very traditional model is you put a set of researchers in one room and they develop algorithms, and when they come up with a better algorithm than you're running now, they hand it off to the engineers figure out how to implement it in production. We haven't gone that way. So all of our researchers they write production code. So it's actually the researchers that own this piece, and they're the ones who are writing the code that's responding within milliseconds to incoming bid requests. So that's the gist of the real-time stack, and then that is fed by the batch stack. And the batch stack is evolved from Hadoop. So we started using Hadoop back in 2006. We were one of the very early users of it, and it was good for the sets of things that I think the developers at Yahoo at the time were wrestling with, and we outgrew it pretty quickly. So we found that once we got up to once we needed to sort about 1 terabyte of data, Hadoop wasn't really getting the job done. So over time, we've evolved various things around it, and the stack here kind of represents all those different contributions. So we've got our own Java API that's built on top of Hadoop. We've evolved our own file system underneath it. So we started with the Cosmos file system, which is architecturally very similar to Hadoop's HDFS, but it's written in C, and we've extended it over time. So it's we've added Reed-Solomon encoding to it, so it uses about half the disk space that HDFS uses. We've tuned the performance as well so that it's significantly faster than HDFS too. So that's where the bulk of our data lives. We've rewritten Hadoop's sorter a couple of times, and we're pretty happy with the sorter we have today. This allowed us to do our first 100 terabyte sort in 2009. And one of our users accidentally did a petabyte sort the other day. We were rather surprised at that, but it turns out our sorter can handle it, which is pretty good. So that's more or less our batch stack. And then on the analytics side, I think this has been we've we've got a lot more innovation going on here, a lot more experimentation, because we don't really have the answer yet. I think this has been sort of the third priority for the company, and it's only now that we're really finding time to dig into it. But we use a variety of technologies that we're evolving as we speak. So we invented something we call Turbo MapReduce, which is an almost interactive version of MapReduce that does quick analyses and quick aggregations for quick answers to things without having to write a lot of Java code. We're using Sawzall as an analytics language that helps out with Turbo MapReduce. So Sawzall is it's a language Google uses, and they open sourced an implementation of it, and we picked that up and we ran with it and we've integrated it into our stack. We've used traditional databases like Postgres and Greenplum, and we've gotten a little mileage out of them, but we've run into challenges with them too. So I think we're still looking to find a really good solution for all the use cases in this area. So, in terms of insights that all this generates, I'll share a few with you. So some of the main insights we generate are ones that we publish on our website. So this is an audience profile for RottenTomatoes.com, and we're showing demographics of the sorts of people who go there. And Rotten Tomatoes tends to skew young. It's particularly rich in 18 to 24-year-olds and slightly Asian. And the audience tends to be the sorts of people who are interested in Media Critic, Hollywood.com, so entertainment, if you can imagine. And they have an affinity to TV stations like AMC, shows a lot of movies, Entertainment Online, and even PBS. There's kind of a shocker. So this sort of analysis is very useful to publishers who are trying to bring their audience to life for advertisers. And that's been the main value proposition that the measurement site has offered, and the reason that so many publishers have signed up for it. Then on the advertising side, this is the sort of an illustration of how our targeting algorithms work. There's sort of two parts of a targeting decision. One of them is who do you show the ads to, and the other is in what context do you try to catch those people. So for one of the campaigns that we're running, company online that sells running shoes, we've got an audience model that predicts they're more likely to be Democrat than Republican, people who buy running shoes, which I think it makes a certain amount of sense. We can't actually tell who's Democrat and Republican online. The data we see is it's all about media consumption online, what sites people are going to. We don't really get a very good signal on this, but it sort of goes to one of the challenges. Once we've built these models, that's kind of step one. Step two is understanding what the models have found. So one way to do that is to take the models and then to project what we found onto spaces that people can relate to, like this. So this is data that we got from a survey company that we were able to stitch into our cookie space, and that allows us to do this projection and describe this audience in terms of this axis. Then the other dimension of this is what sites do these people tend to visit, and this is a good place to reach them online. If you catch even an avid runner in an environment where he's not at all thinking about running, he's much less likely to buy the shoes you're hoping he'll buy. So this is the basis of our placement targeting, identifying likely sites online that we're going to be able to find people like this. And then this slide sort of illustrates one of the challenges that our business and that the industry has. And one of the reasons I think Quantcast is a particularly interesting place to do this sort of thing, that the challenges are so multi-layered. I mean, from the architecture stack, we've got very low-level systems problems keeping our machines up and running. We've got network problems. We've got challenges in the data processing stack and in the machine learning itself. And then on top of that, we've got political problems like this. So we're doing display ads online, and most of the money, or a good chunk of the money that's getting spent online, especially by performance advertisers, goes to search. They're very used to buying search, and they're used to evaluating search based on who's clicking on the ads they're running. Well, it turns out clicks are not a very good metric for how well a display ad is working. But it's very hard to talk these people out of clicks because that's what they're used to. But this is one of our challenges. So what we figured out is that people who click on display ads are just not the people who are going to buy your product, almost no matter what your product is. They're typically people who are low income, they're often unemployed, they're minorities, they're under 12, they're sitting around at home and they have nothing to do but click on ads. And you can see that from the demographic analysis here. This is one of the messages we're trying to take out to the market, and that a lot of people in the display advertising space are trying to carry as well. We can bring it to life with our data, but that's only part of the problem. We still have to convince them. And with that, I'm going to turn it over to Mohammed.
So I'm Mohammed Sabai. I work for Facebook. I actually joined pretty recently, like a couple of months ago. I used to work at Facebook. I lead a data analytics, and I'm sorry, can everybody hear me in the back? All right. So I actually manage the analytics and data science team, lead a bunch of data scientists for three things, basically. One is privacy, one is timeline, and one is OG, which is Open Graph, which is where, it's ramping up on Facebook. And Open Graph allows you to, if you're on Facebook, you see like Jim is sharing, he listened to Metallica on Spotify 2 days ago, things like that. So, Spotify. So prior to that, I was at Netflix, where I was a data scientist working on things like personalization, how to recommend the best movies to users and improve the search experience. Prior to that, I used to work in a world similar to what Jim and Ron are in, which is I was this company called Fox Audience Network, which one of the properties they had was Rotten Tomatoes before they sold it off, and they had MySpace and Wall Street Journal and so on. And it's very similar to what what Ron was and Jim was, actually what Jim was saying here earlier is, I agree with him 100%, which is clicks do not tell the whole story for display ads. So I worked on a bunch of products for display ads at Fox Audience Network, including something called hyper-targeting, including behavioral targeting and so on. And before that, I was at Yahoo Research. So in terms of the architecture, so I won't go as low level or as detailed as the other speakers here. But I just want to give you a context. And I've worked in multiple places where the data has been big. And as Ron was saying earlier, the problems and the solutions are very similar in many respects, in many areas. So I'll go through a couple of things here. So in terms of, this is a user base. And this is the last release numbers that we had for Facebook, which is 955 million users. So, it's like, if you look at it, it's only like 45 million less than a billion. And this number was in May. It's actually pretty close to a billion now. We are getting there. But if you look at this plot here, and this gives you an idea of the scale of the data that we deal with here. If you look at the plot, these are not actual users that we have plotted here. What we have plotted here is the friend connections. It's not coming out very clear. And the longitude and the latitude have been plotted on this plot. So that is what you see where the users are. You see India there, you see US, Canada, some part of South America, very sparse in Africa, nothing in China, some in Europe and so on. So, and the challenge here is, many. So it's not just the number of users. Remember, at Hadoop Summit, there was a speaker who introduced, what is big data? Big data, if you remember a mantra, it's made up of three things, TIO. Transactions, interactions, observations. So all these users are actually interacting, and you know it very well. These are actually sticky users. They come to Facebook, I don't know, like they're always on Facebook. They never leave Facebook, and so we are capturing all these transactions that are happening at the same, for these users. And half of these are daily users. So I should have mentioned that. So this 955 million is monthly active users. What that means is these many users signed in to Facebook at least once in the last 30 days. And half that many users, about 500 million users, are daily active users, which is, these users come to the website daily. So this is another higher dimensional data set that we have. So one was the number of rows that you have, which is 955 million. But then along the other dimension, you have these other activities that the users are doing. I may be liking a fan page. I may be liking a Metallica page. I may be liking a sports page, right? I may be commenting on somebody's post. I may be updating my own status. I may be sharing something. All those are actually accounted for here. So this number is actually from 2011. This number is even higher. So on an average, it's actually over every month, the users spent 700 billion minutes on on Facebook. Again, this number is approximate because this number is back from 2011, actually more than a year ago. This number is much higher than this. I was talking about sharing of content. We have 30 billion pieces of content shared every month. Again, these numbers are old. And when I say content, you can actually think of, photos. Well, photos is different. Apart from photos, every piece of content that is being shared, which includes your links that you're sharing, status updates, and so on. There are 2.5 billion photos uploaded each month. So you see that number, billion, come again and again. It doesn't really strike you. You see Mark Zuckerberg in the center there, right? So, but this is if you look at in a traditional machine learning sense, if you look at the columns, these are the columns that we deal with. So you can imagine, it's 955 times a few billion, a few hundred billion, or a few million billion columns. So this is the scale of data that we deal with. So this will, and one more thing on the data size. This again is back from 2011. You can see the rate of the growth of the data in the Hadoop cluster that we have. It was 50 petabytes last year, and it's growing, right? And just to give you some number, last year at this time, we had about 500 million users. Now it is, the number I said is 955 million, million, yeah, close to a billion. So you can imagine the size of this data. Now, I'll go into the data architecture flow, how it takes place at Facebook. So we principally have, we have two data centers, one on the East Coast and one on the West Coast in Oregon, and we are trying to set up another data center. So if you look at the data flow, we actually have data coming in from two different sources. One is the static data, not static, meaning these are data from the advertiser's point of view and from the user's point of view. So this will be information about my own user history, actually my own user demographic information, and all the campaigns that we run. So this is coming from a MySQL tier. And then we have transactions that the users are doing, which is actually collected through a scribe layer. So this is the layer of federated MySQL, that is the static layer. And then you have the scribe layer, which is collecting all the transactions that the users are doing, all the interactions, all the interactions that are happening. So this data flows into our Platinum Hadoop cluster. We call it Platinum Hadoop cluster. And this latency is about less than 15 minutes. So every 15 minutes, we gather all the transactions that are happening. And this data from the MySQL is actually poured into this daily, once a day. So this data is actually out of date by 1 day. And this has information about the ad campaigns, for example, static information about ad campaigns and static information about the users themselves. By the way, this doesn't include, so before I move on, I should say that we actually train online models for predicting the click-through rate of ads and so on. So this actually lives outside. So this is actually a Platinum Hadoop cluster, is our central repository where all the data from production is actually kept. But we don't run queries on here. We have an ad hoc cluster called a Silver cluster here, which is replicated. So once the data is here, every 15 minutes, so every once a day, it gets replicated out into 3 places. One of them is the Silver cluster, from where all the data analysis, all the data analytics, all the machine learning, all the data mining that we do is done in here, in the batch processing mode, in Silver cluster. Even in online, we actually use that Silver cluster and push it to Platinum. So from the Platinum cluster, it gets replicated into 3 places. One is this Silver cluster, or an ad hoc cluster. One is it goes back to MySQL for reporting on the advertiser side. And the third place is Oracle Rack Layer, or MicroStrategy, Tableau, name it. All the reporting stuff happens here. So there is a bunch of ETL processes, which I'm not showing here, that run both on the Silver cluster and the Platinum Hadoop cluster. So so this is what I'm going to be focusing on here, which is the data flow that happens from the way transactions are done all the way to the ad hoc cluster. Now, before I dive into that, one thing I should point out is there is a lot of algorithms that we run that depend on this data being real time, and for some, actually it needs the data to be present even though it's a day old. So, for example, you may have when you go to Facebook, you will see friends you may like. We recommend friends to you. We recommend pages that you may like. We recommend ads. We show ads to you, and so on. So the whole the reason why Hadoop is so powerful in this is because there is no other system that we know of currently that can deal with this scale of data. Two, we have to do analytics and algorithms at the same time on a data that is this huge. If you do sampling, you run into other kinds of issues. And the sampling here, I mean, even a one-person sample is like a few million users. So you cannot really depend on sampling, especially for analytics. So we came up with this a non-technical way. So for people, so we actually, let me go back here. For algorithms, we use most of our jobs actually use Hive, which I'll go into in a bit. But we also use Java, and we also use Pig and Scalding these days for coming up with these models and for analytics. Now, Hive is something that we came up with that actually tries to abstract out the MapReduce from the users. So even if you're not trained in MapReduce, even if you're not trained in Java and Pig, and all you know is SQL, you can still write queries, and internally it does MapReduce. So it gives you a MapReduce execution on top of it without you actually knowing about it. And there's a library that we have that combines. There's a Python library that we have that combines Hive with MapReduce. And there is also this layer of UDFs, or user-defined functions that you can write. You can write the same thing in Pig. You can do the same thing here, and you can write actually pretty sophisticated algorithms here. Not the general k-means, but you can actually do something very sophisticated in these UDFs. As I said, 95% of our jobs use Hive. This is another. So if you want to get even less technical, so this is another layer that we have for people who are not familiar with joins or inner join or outer join and things like that. And this actually is a tool that we have that allows you to do that from a UI. So we have this tool called HivePal. Now I'll go back to this. So there is a bunch of things that I haven't shown here, which actually do real-time analysis on top of the batch mode, which is Silver cluster and the Platinum cluster. We don't run actually any heavy processing on the Hadoop, the Platinum cluster. All our stuff runs on the Silver cluster. But there is something called Peregrine, for example, and a bunch of other tools that we have that do real-time analysis. So they bypass the Hadoop pipeline. They don't use MapReduce, but they still allow you to get pretty accurate answers on a sample set. And then we have other systems. For example, you are launching something, a new feature. You want to proactively, measure if things are going down or going up. So we have a different system that allows you to, before data even lands up here in the Platinum Hadoop cluster, there's a fork that gets created of the Scribe Hadoop cluster. There's multiple systems, which I'm not showing here because the diagram would have been very complicated. So those forks actually allow you to bypass Hadoop and measure something or get real-time information. Now I'll go a bit more into my area, which is machine learning here. Now, one of the things that you see is with these data sets. I mean, there was a paper that came out, I think, 4 years ago, that said that you don't really need sophisticated algorithms. You need more data. I forgot the exact title of the paper, but and that's actually partly true as well. So with this kind of data, you don't really need to get as sophisticated. You still need to get sophisticated, but what I'm saying is there's a lot of low-hanging fruit if you just take some simple approaches and throw at it a lot of data, As an example, collaborative filtering. Collaborative filtering is something that is easily amenable to MapReduce, and there you don't have to worry about sampling. Then you talk about iterative algorithms. You talk about, let's say, do you want to do topic decomposition or want to learn topics or clusters, right? You can easily use LSA. Mahout has an LSA implementation that you can use. You can write your own. It's not difficult to write. And there's actually multiple implementations of LSA, for example, that will give you a very close to exact answer and then you can use all the data set that you have. And one more thing that you want to avoid in sampling is, if you sample, you don't capture the outliers, which are sometimes very useful. You throw out the outliers, which are actually very useful. And in a case like in a case of Facebook, for example, we have trends. For example, Ramadan just ended, right? And we saw a lot of trends. Olympics was on. We saw a lot of trends around that. So Those are things that you want to capture with as little sampling as possible. But when you do iterative processing, for example, when you're doing LSA, for example, or LDA, you have to be careful about what gets pushed to the next stage of the mapper. So you don't just write MapReduce code and forget about it. You have to optimize, think of optimization from the very word go. And the second thing is, if you're doing iterative processing, you have to be careful about how much data you're pushing to the next stage of the mappers. So the way iterative processing works is you have a MapReduce and you have a master script that actually controls how many iterations you want to make with some convergence conditions. So let's say you do 20 iterations. Now, at the end of it, you want to push the latest data set. Now, each mapper is actually going to process only a subset of lines. So let's say there's 100 million rows. Each mapper will only look at, let's say, 1 million rows or 2 million rows. Now, and based on that, it will learn some function. It will learn some weights. Now, those weights go on to the reducer. Reducer sees all those weights coming in from different mappers, and then it recalculates. Think of like EM if you want to get an intuitive idea. And then once those updated weights are, once the reducer learns those new weights, it has to make sure that these are updated and these these get pushed to the mappers for the next stage. But that is very important. So the important thing to keep in mind is you are not pushing too much data. So you have to optimize. Other things you have to optimize is, you may want to use combiners. You may want to compress the map output because reduce copy is a very expensive operation. So basically, the moral of the story is you have to. There's ways to do it right and there's ways to do it wrong. So if you are in the MapReduce world, you have to think about optimization many ways in many respects, not just And then the other thing that you have to be careful of is, are you optimizing the right metric? Maybe in some cases you may not really need the exact answer. You're fine with, given the size of the data, you're fine with an approximation that actually gets you, very much close to the end. So, I think I'm out of time. So I'll welcome all of you to this meet, and I'm open to taking questions. Thank you.
Let's do it differently. I think what I want to do is I'll try to kick off the question period and ask 1 or 2 questions, and then I'd like to try and get the other room in after that and let them ask a few questions, and then we can come back to our room. So my initial question is, what do you think is the biggest change that is underway right now, especially in connection with machine learning parts of these platforms? I see one big change happening, a movement towards more real-time action. And we even see some companies trying to push a little bit of a revolution in Hadoop, like MapR has re-engineered big chunks of Hadoop, driving it towards being able to do real-time kinds of things. But established companies are probably heavily invested in the original Hadoop, and maybe, I don't know, are they starting to look at things like what MapR has? It seemed like some of you have already done things like what they did yourselves. But do you see, so that's one possible big change that is happening, but maybe you see some others that are just as big.
Sure. Well, I think that just the very shift to big data techniques is the big story, right? Absolutely, big data itself is new, and there's a lot of activity in all that white space. All the things that people are looking at, how do we solve this, is up for grabs, right? There's a lot of open source projects. There's a lot of well-funded startups that are looking to bring a piece of value to the puzzle. So I think the big trend, though, is this shift from 1980s database architecture to big data, where you have the ability to store unprecedented amounts of data, as we heard about here and some of our customers are doing, and make sense of it and start to automate decisions that were being made manually and slowly, creating a ton of value in the economy. I think that's the big picture here. Now, down the detail of how are big data platforms changing in the architecture layer, certainly real time is a popular thing to put out there, right? We see a role for both batch and real time in a lot of systems that it really does make sense that you can get a lot more efficiency out of doing sequential processing. The way spinning disks work, it's more efficient to do scans of data rather than random access. So there's going to continue to be a real value in micro batch architecture for the foreseeable future. There's definitely more up for grabs in terms of, well, what are you going to do for real-time big data? Is it just going to be some NoSQL? Are you going to have some distributed search with Solr? Are you going to have a full platform like a Storm or some of the competing techniques? Is it going to fold into Hadoop itself, whether it be like with MapR's approach or some of the startups like Age Streaming that are trying to do it? That's up for grabs, and I think that is a second order evolution, that as companies get a lot of value out of big data, they look to speed it up. But I think the fundamental thing is that the system, the ecosystem is moving quickly, and higher level capabilities are building on top. So I think especially for this audience, probably even more important than the evolution of new platforms for the architecture are higher order toolkits and capabilities. Right now, if you want to do a lot of data science problems, if you want to implement algorithms, it's often a lot of hand implementation and tuning. So there's a lot of work that goes into implementing something. You take a Mahout library, it's pretty immature, and using it tends to involve debugging it, kind of getting it working for your problem, hopefully contributing something back to the community. But we see that needs to shift and is shifting, that there's going to be more investment to have better building blocks so you can spend more time thinking about what's my problem and less time debugging and efficient implementation of it.
Well said. I think there's a lot of new stuff going on, but I would characterize it as more quantitative than qualitative, in the sense that Hadoop did an amazing job at making it possible to solve a certain class of problem. I mean, where there was nothing before, there is now something, and that's a big qualitative shift. And I think that's opened the door for quantitative improvements on a whole bunch of different dimensions. So, real time, it's a quantitative shift. It's reducing the latency, and who doesn't want less latency? That's a great thing. We're like a lot of what you're referring to, Ron, is about accessibility, making that technology more accessible to a broader variety of organizations and people with a broader variety of skill sets. Quantcast has been focused on efficiency. I mean, we were kind of from the start, we had more brains than money, perhaps more brains than sense, and we wanted to get the most processing out of our hardware because we didn't have a big hardware budget. So that's led us down kind of the development path that we went down. But everybody wants more performance per unit hardware. So ultimately, that's something that's going to be in everybody's best interest. So I think there's this diversity of dimensions that the technology is improving on now, and I'm more aware of that than the next big qualitative shift.
Thanks, Jim. So, I see four things that would, that things are moving towards. One is privacy is becoming more and more important. So, especially, with all these mishaps that have occurred over the last 10 years, maybe last 7 years. So, when you store data in Hadoop, I think anonymization and things like that are going to be more and more important. And it becomes a challenge when you're actually joining data sets across multiple, when you're joining data sets across multiple sources. So, the second thing is, I agree with, and actually in Facebook, I agree with the speakers here earlier, which is, real time is important. Actually, at Facebook, we are doing a lot of real time machine learning model building because it's a need of the hour. You actually have to capture short-term signals right there, rather than wait for batch mode. The third thing actually, which is lacking, I think, in this data infrastructure is, or maybe it's not as developed as data visualization. That can get better, and I think there's a lot of effort going in that direction as well. The fourth thing would be, a mature, of course, MapR is getting into it, but a more mature mathematical library that runs maybe on Hadoop, maybe outside of Hadoop, but that can scale up. Right now, the only thing that you have is, you have MATLAB, which tries to do its job. You have MapR, which is trying to do it on Hadoop. But with more and more computing needs that we have, especially around, let's say, matrix operations, something like that, you have to be able to scale it up. So I think that's where more and more you'll see a lot of work happening over the next, let's say, a few years.
to the other room. Let's have a question. Hopefully we will be able to hear it. We can't hear anything yet.
Hold up a sign.
Are there any questions in the other room?
Yeah, my question is for Jim Carrey. That how will you compare your Quantcast with company like Blue Sky? Thank you.
How would I compare Quantcast to Blue Sky? What Blue Sky does is they've been focused on collecting and reselling specific data segments that are of value to advertisers, and that's been a model that has worked very well for them. I think their challenge is that the scale of that approach is sort of limited. What we're doing is kind of the generalization of that. We're in the sense that we're trying to take whatever target the advertiser's after, and then figure out what signals predict that among the behavioral signals that we observe. So our model is about, we have advertisers put our tag on like the thank you page at the end of their shopping cart, and then we go and statistically figure out what do those people look like and build a custom model for the advertiser. Blue Sky is much more about kind of standardized channels and standardized segments, so that if you're an automaker, you can buy cookies that will get ads in front of people who are in the market for automobiles. We're trying to be more generalized than that.
Okay, let's have our next question from this room, but I'd like to encourage people to focus on or steer towards things that involve data mining, since this is a data mining group. Okay, let me see. So the question is about quality of results. We've had a lot of information about flow and the architecture of these systems, but maybe there's not enough evidence about the quality of the machine learning results or whatever.
Or the quality of the advertising, I think, is the thing.
So maybe each of you could comment quickly about the evaluation methods that you use for your data mining results.
All right, so we actually do multiple layers of evaluation just to measure the quality. So you can actually do offline evaluation where you have a standard holdout set, like cross-validation kind of thing. Then you can have a test set, right? That's standard machine learning. But even before you go into production, so you can actually have multiple metrics. For example, if you're looking at search, you may actually measure offline some metrics that you care about. The DCG, it could be map, or if it's recommendation you want, if it's ranking you want, you can measure a bunch of things as well. Let's say map, mean average position. Now, once you go into production, so that is going to be very important, is how you, first of all, one is how you run the test. The test has to be designed properly. So there's experimental design is actually very, very important. So, and there's multiple layers. And the reason it is important is, let's say at Facebook, we have, 10,000 experiments running at the same time. So when you get back the results, this user may have been exposed to, 1,000 different cells, 1,000 different versions of different algorithms, and each is trying to measure different things, right? So you want to be able to, make sure that one test results does not spoil the results of the other test that is running. So first, experimental design is very important, timing around that, and how you interpret the results. So those three are very important. So, so just to recap, there's multiple ways that you can measure the quality, but I think the best test is a bucket test. I mean, nothing beats that.
I'm just curious, following on to that, do each of you have an experimentation platform? That's something that you do all the time?
Oh yeah, absolutely. And we're, I mean, I think Mohammed described some of the challenges pretty well. It's really important to have a good experimental framework for analyzing new ideas. And we've always done a lot of that offline, and we're continually building and rebuilding the tools to help us do that. And we found it wasn't good enough, that really, for at least the ad domain, we needed to get experiments running on live traffic before we could believe the results. And then ultimately, it's the advertiser that tells us whether the thing worked from their point of view or not. And their attribution mechanisms are not very good at all. I mean, it's like the old John Wanamaker quote, "I know half my advertising is wasted, I just don't know which half." It's probably much more than 99.9% of advertising is wasted. And that's a shame. That's one of the things that's really excited me about working in this industry. If you look at an average TV show, it's 60 minutes long, and 20 minutes of that is ads, because they can't target the ads decently. If you could improve that by a factor of 10, which seems eminently doable, you could get 58 minutes of TV and 2 minutes of ads. That would be a beautiful thing.
And I think big. I definitely want to bring the perspective that we do a lot more than just advertising. That we also help customers do things like just detect malicious bots that are threatening and security of the internet and people's computers. We've been doing work on helping with customer recommendations in retail and for credit cards, helping with automating response to incoming support events for devices, right? So there's a big world where these models apply. And of course, absolutely themes of assessing quality are really important. The way I look at it is there's different kinds of problems that you tend to work on, right? There's problems on the one pole that are incredibly deep and you're never going to stop investing in, right? And I think the quintessential example of that would be Google investing in search, right? Is Google going to ever stop and bang in their competitors, right? Is anyone in that space going to stop investing in driving improvements in search? Of course not, right? It's hundreds of billions of dollars at stake, and so you have extremely sophisticated, specialized frameworks. The other extreme, though, is you've got a whole family of products, capabilities, offerings, features, and you want to do just enough work to test them and validate them and integrate them in and then move on. And that becomes a very different kind of validation framework where you need to have the ability to quickly enable somebody to work on a small problem and validate it's going to work. And all of this is about incremental commitment, right? This whole notion of data agility. It starts with how quickly can I prove the first idea was wrong and refine it? And you go from that to exploring the data to finally having a model that you think is going to work, that you've got good evidence is going to improve. You can simulate it in your test environment. And finally, you do the bucket test, the A/B test. Now, the interesting thing, too, is there's some domains where you have enough information about what's going on anyway that you can simulate pretty well if I chose different behavior, what would happen. So if you think of search, if you looked at, well, what paid search ads might people respond to, you might have some clue from organic search what's going to work. But there's other cases where if you don't take the action, you're really working off a very limited data set about what might happen, right? That if you don't present users with an option, if you don't ever take an action, you're very much conjecturing what's going to happen when users see this. And companies often respond by having some kind of control or random or some kind of learning period where they throw something unknown in front of a user just to see what happens, right? But that's also waste and inefficiency, right? So how can you be more efficient at minimizing the cost of learning and still be able to find new things, right? So I think it's a problem that in the general case is complicated, but absolutely, I mean, data, the quality of the models, driving efficiencies and improvements is the name of the game, right? It's why there's this opportunity to apply data in a new way in big data environments.
So I just wanted to add a couple of things here. So you have to have very mature analytics. So that's the other thing I should have stressed more. Machine learning and model building is fine, but you also have to have, have to have a very strong analytics platform where you can, monitor things as they are rolling out, so you can capture things proactively rather than the users complaining. So the code, for example, has to be instrumented very well, and you have to have the right metrics that you are looking for. So that is one. And the other thing I want to stress on, it's not just the quality of the model, it's also performance-driven measures, metrics that you want to track. For example, how is the time, TTI, for example, or how much time is it taking, the server response time. When you launch something, is it true that suddenly the users are unable to upload photos, for example, things like those. You have to be able to capture. You have to have a very fine-grained level of analytics that runs on top of it. So, yes.
Okay, let's try to take another question from the other room.
Do I press this button over here?
Yeah, you're on. You're on.
Okay.
Just go.
Hi. When you look at the cost of these analytics infrastructures and the big data clusters, can folks comment on where is the cost? Is it on the hardware? Is it on the software stack on top? And then after this, as things are scaling, where do you see there being some concerns in terms of limiting like stress points in terms of the infrastructure cost? Thanks.
Right, I'll start and try to go quickly. I think the general rule of thumb in budgeting any kind of system has been a third, where a third of the cost probably is hardware, a third is software, and a third, of course, is services to help you implement it successfully. And while it's true that last year when the Forbes article on big data said 44% of the revenue in big data services, but because it's a little less mature space, right? There's a little more help needed. But the point is that it tends to be an even mix, right? That we see a lot of people say, hey, well, let's run ahead and use open source, right? So some of the companies here don't spend a lot on software support because they do it themselves, right? So they really have internal cost of resources, right? But most of our customers, most of the enterprises are looking to license software and get support from vendors so that they don't have to build their own internal support teams for the technologies they're using. The technologies scale amazingly well. Let's be honest, there aren't a lot of companies that face scaling challenges like the gentlemen here have or Google has, right? So these patterns, these architectures, or Yahoo, have scaled so far out and have solved such tough use cases that the kind of scalability question, there are not a lot of cases where it really becomes an issue. There are cases where the economics can be in doubt, right? I mean, if you want to archive a few exabytes of data, it will cost you something. We've talked to customers about that, and you have to think carefully about, do you have the business model support it? So those are a few quick observations.
Yeah, as you say, we've spent a lot more on hardware than on software. Maybe we didn't buy Oracle. That might be one reason. In terms of when you're planning out hardware, what do you run out of first? We're actually doing that for next year right now, and I think my answer is spindles. How fast we can get data out of the Hadoop cluster sort of depends on the seek time of disk and how many disks we have. So just projecting out how much disk space we're going to need next year and how much CPU and how many spindles, the most expensive part for us is making sure we have enough spindles.
So just to add, I agree with what Ron and Jim said here. Just to add to that, it actually depends on your needs and how you project it to the future. For example, I've worked at companies where we didn't have, for example, Netflix doesn't have it had its own data center, but now they have moved everything into Amazon cloud. By looking at the data efficiencies that we get that way. There are companies who are doing the reverse, which is they were in the cloud earlier, in like Amazon EC2, for example, or Microsoft Azure, and now they are coming up and creating their own cluster, their own data center. So, it really actually boils down to the data set that you have, the problems that you have, and the scale that you see in the future. The other thing that is important to keep in mind is, some people, just because Hadoop is a buzzword these days, some people just jump on it, but that should not be the case. You have to think carefully, whether Hadoop is the right thing. In many cases it is, but whether Hadoop is the right thing, right solution for you.
I want to follow on that. So Netflix moved into Amazon, and that was kind of shocking to a lot of people because a lot of the conventional wisdom was that you want to build your own. The economics make it make more sense for you if you're getting pretty big, but their idea was that we don't want to do any heavy lifting if it's not core to our business, so why don't we just let Amazon do all of that stuff?
So many reasons, actually. There were many reasons for doing this. One is you don't have the headache of maintaining your own cluster. You don't have the headache of having, say, data centers set in all the different places in the world. Right now you are actually leveraging Amazon's data center, which is pretty good. Third is, if there is any maintenance issues, you don't have to deal with that. So you save a lot in those respects. And then if you look at it, there is a data if you had, and then there's the hiring piece of it. You actually had to hire people, system engineers, system administrators, Hadoop experts, who would actually maintain it. And so there's all those reasons. On the other hand, what do you gain? What you gain is efficiency. For example, what Netflix had, it actually had to copy its data was actually getting logged. It actually made the switch to the cloud much earlier than switching all its data center, all the logging infrastructure over to the cloud. Now, all the data was already there in the cloud, and now you had to copy all the data over to your data center. So there's a lot of inefficiencies there. So right now, I mean, as far when I left like 2 months ago, so till that point, and the projection that was done at that point was, it's actually a better solution, both in terms of saving time, space, and money, more importantly. Sorry? Say it again? It would have to. Oh, I see. No, really. No. They just keep the data there. They have their own. They have the full stack. Yeah.
Let's take another question from this room. Go ahead.
And good questions they are. I'm not sure how to answer you quickly. Storm is working for us and this one use case. We haven't used HBase, but we may in the future as we get more into scenarios where we want to be doing more update operations. There are not a lot of updates in our architecture today, but there probably will be in the future.
Let me speak briefly and let Mohammed wax about the use of MySQL for low latency. I think that there are some great options out there. So we think the way that most companies to date have done big data solutions with low latency is to a blend of heavy lifting for efficiency in Hadoop with batch processing, then pushing data in to NoSQL environments. And the ones we see the most are probably Cassandra and HBase, but there's a number of other obviously popular ones, often coupled with the use of Solr for distributed indexing, because so often the NoSQL databases give you low latency lookups, but you want to do faceted search, you want to have more complicated, query-like capabilities, it turns out, for low latency. So in a lot of those use cases, those are technologies we see working well. Storm is an interesting new technology, and there's a number of other approaches, but it seems to have some traction, where it's giving you a kind of distributed infrastructure for low latency. So you not only get to scale out the data, but also have an easier fabric for where you run things. So as companies are doing more and more low latency big data, it's creating value because it's painful to manage like lots of little servers that are running this service, and you start saying, well, let me just start scaling it. We're just getting started using Storm with a handful of customers ourselves, but we think there's promise there. And the open question is going to be, is that going to be the platform, or will, for example, the use of Yarn with Hadoop, where you have a scheduler that can schedule other applications on top of that infrastructure, become more popular, or any of the dozens of other competitors that are out there in the world?
So that's let me take a, so in this case, I'm not really sure what your question is, because it can actually be answered at many levels. So one, are you saying, should we have used MySQL, or are you saying, should we have our own data center? So remember this. Mm-hmm.
So we should probably repeat.
So remember, this is
other people can't hear. I just remembered.
Okay. Can you hear me now?
No.
So
the other people can't hear him.
Oh, sorry. So the question is, if Facebook were to redo the stack, would it do the same thing that we showed earlier? It's a hard question and really out of my expertise. I won't really, but what I would say is, what it allows you to do is, if you have your own data center, is it allows you to optimize a lot of things on your site. And Facebook actually runs its own data center, where it manages its own data center as well. So would we have used MySQL? Frankly, I don't know the answer to that. Would we have still kept the same architecture? Yes. I mean, this architecture makes sense that it has been an evolving architecture. But if you think about some of the core pieces here, I mean, I wouldn't, I wouldn't venture in that direction. I don't know. Sorry.
Well, I think we should go to the other room now. Do we have a question from the other room?
Yeah, hi. Let's assume that you want to be a startup in this space somewhere, and maybe you want to be providing services to somebody setting something up in the cloud. What is a business model wherein you make some money that's proportional to something, or even better, more than proportional to something?
I think that's probably too hard for our panel here. So, let's take another question from here.
Perhaps there goes my billion.
Okay, so the question is, how do you handle data exploration?
Well, we have explicit data retention policies. We throw out anything that's older than 13 months in the current policy. It kind of ages, given the domain we're in, it ages out from under us anyway, because cookies are constantly churning and being deleted, and cookie lists from 6 months ago aren't really relevant today anymore, so there's not a lot of value to get out of them. I mean, the main value is to keep things around for historical analysis, and 13 months is plenty for us. Does that answer your question?
I'd definitely say we have customers that are looking at it differently, that they want to retain years of data, that they're excited, like, we can only keep 13 months of data in our Teradata cluster, and we'd like to keep 7 years of detail in our Hadoop cluster so we can go back to deep history and mine it. So, I mean, it's a different industry, right? I mean, that's a large retailer that's taking that stance.
So I think
remember, he works in privacy.
I think I'll try to rephrase the question that we had from the other room, and maybe maybe you'll be willing to answer, but feel free to shoot me down. So where do you see the opportunities for data mining and big data in the near future? Do you see anything really big there that maybe you're just not able to work on because you're so busy at Facebook or Quantcast or whatever? Nothing you want to give away, huh? Or maybe this is...
No, I mean, I think there's tons of opportunities in this space, right? I mean, it's fast moving. There's, it's not as simple. I firmly believe this is more of the era of the project and the product, that it's time for to build complex, differentiated solutions. That's where the action is. I mean, you heard the pioneers in the space have created really unique architectures that create a lot of value for them, and even a similar company, Facebook and LinkedIn have some similarities, but their architectures and the way they're harnessing their data are radically different. And we're seeing that happening across many industries, right? So it's still the time for picks and shovels and platforms and toolkits and libraries. I think that's really where the action, the excitement is, far more than at the level of, we've got big data in a box or in a cloud, just upload your data and we're done.
Let's take another question from the other room. Do we have any more questions from the other room?
Yeah, hi. Can you tell me what technologies and tools are you using for real-time search, and what are your practices, best practices? Thank you.
So the question is about what are you doing for real-time search?
Well, I think this is a problem we haven't. We don't have a general solution for yet. We've sort of defined very specific search problems that we can answer in real time, and I see this as sort of an industry challenge, and a lot of the focus of a lot of the startups out there is to figure out how do you bring more general query capabilities to big data, and I think there's a lot of promising solutions out there. But Ultimately, I don't know the answer, so I'm looking forward to what Ron says.
We saw a talk recently by Osama Fayyad, who used to work at Yahoo, maybe when you were there. But he mentioned that one thing that is one of the most interesting things that he saw happening, where they got some insight that they didn't expect, was when people were doing searches that didn't result in any answers being returned. And it was because they weren't really expecting people to be looking for that kind of product on their website or whatever. But then once they realized that was happening, they could go out and get some of those things and put them up.
I mean, I talked about solar before, and I think some of the interesting opportunities are around taking and scaling and making reliable and distributed technologies like solar and Elasticsearch, right? So we see innovation happening. DataStax has done a nice job of integrating solar onto their Cassandra backend to have a more resilient, scalable, but commercial solution. We're doing some work on extending Lucene and then solar to work on top of HBase with coprocessors. And we think there's other investments happening. So solar seems to be a very popular API and technology for doing search, but to make it scale is still very much an open question as to how that's going to work out in the market.
And let's come back to this room and have one more question, but I want a question that intersects with data mining somehow, not just platform.
So recently, Microsoft
Please repeat the question, whoever answered.
Sure. The question is, Google and Microsoft have started, correct me if I'm wrong, Google and Microsoft have started investing a lot in audio, getting features from audio, right? So the general question is, will features from audio improve the model? That's a hard question, if you look at it. The same applies to video as well. So these are good signals to have, but there's a lot of noise also associated with those types. So we haven't done any work. Well, I'm not aware of any work that that actually is state of the art. That respect that. Is that a paper? Okay. I haven't read that paper, but what I would say is, in terms of we had tried that at Netflix to look at, for example, the subtitles and things like that. So in some cases it gives you a good signal, but in some cases it actually, so you have to be careful features out of it. And deep learning in general is very good. Deep learning is actually things that people are using. Actually, in Netflix, one of the things that we use that came from the Netflix prize is a Boltzmann machine, right? So we are doing things like that, but at the level of audio and visual, that is something that that's not my expertise. So I'm mostly focused on the text.
Let's try and take another question from the other room, and that will be the last question there, and then we'll come back here for one more question.
Hi, Michael Hummel, CEO of PowerStream. My perception of Hadoop is that it's that popular because it was the first solution which actually scaled and made it possible to analyze big data. But my statement would be that Hadoop is, regarding data structures and algorithms, let's say highly inefficient if you compare it with other technologies. So I actually see a bright future for other approaches to analyze big data, especially if you look at the amount of infrastructure and the energy consumption which is needed to run a Hadoop cluster. I would like to hear your opinion on regarding efficiency of Hadoop processing regarding other approaches.
But there's no machine learning component to that? or data mining. I don't know that our experts here are really the right people to talk about that, but
I can throw in a real fast answer, so it gives you some room for more machine learning. But I'd say that I think that it's become a very effective starting point and a foundation that's being optimized and improved. It's not the answer to everything. It's not world peace, but it's a great foundation, and it's going to be hard to beat the momentum that it has as a platform.
Okay, we'll take one more question from this room, and please make it intersect with data mining somehow. We have several questions about data that is of very different kinds in different formats and even in different languages.
So I'll answer the simpler question, which is multiple languages. There was a related question on audio and video, which I'm not an expert to talk about here. So I'll probably skip that piece if you don't mind. But for languages, we actually have, we support, we build models for multilingual features as well as single language features, right? So that is already taken care of. Was it a question or was it something else? So the same user, for example, is speaking in Chinese, English, right? Right. So Facebook is, yeah, that's a good point. But people can still speak Chinese, I think, in Facebook. Yeah. So what we have seen is for the majority of the cases, the users actually predominantly speak one language, but there are cases when they speak two languages, yes. So in those cases, we build one model where we take, let's say, tokens from each language as a feature, right? But I'm not aware of any work. I'm not an expert on this. I cannot really comment on how we combine, let's say, treat this guy more of a Chinese versus an English speaker. It could be based on the model itself, because remember this user has a distribution. This user has the property distribution of the word that you are, or the token that you are after, right? But I think your specific question is, how do we balance? How do we, let's say, do a explore exploit kind of thing with different languages? I'm not the best person to answer that. Again, I'm not the best person.
Okay. Well, I'd like to thank our speakers.